Hello guys, Dr. Hasbullah here, and in today's video we're going to be looking at turbines, okay? And in the very beginning of this chapter, I've explained that a turbo machinery composed of two types of equipment, which is the equipment that supplies energy to the fluid, and there's an equipment to extract energy from the fluid. So if you have here a rotor and you have fluid here, okay, and you have equipment that supply the energy to the fluid, alright, and this is called pump, right? And if the medium is air, you call it compressor. And if the energy is transferred to the rotor from the fluid, meaning that the device, the turbo machine, is actually extracting the power from the fluid, and this is what we call turbine. Okay, I'm sure that you have heard of hydroelectric turbine before. So that's basically a turbine. So water that has a very high potential energy, it goes into the turbine, rotates the wheel, okay, and then that wheel, the rotation, is connected to the electric generator. So that's how you transfer the energy from the fluid to the mechanical rotation to the electrical power. And for turbine, there are many classifications that you can do, right? So a turbine can be classified according to the shape, okay? For example, it could be axial turbine, where the water goes axially, right? And then it could be radial turbine, where the water goes into the turbine and turns the direction to the axial direction. So that is called radial turbine. It could also be a mixed flow turbine, where the water comes in between the angles, in between the horizontal and vertical position, right? So that the water comes at an angle, right, and goes out at axial direction. Okay, and that is one way to categorize it. But in this course, we're going to categorize the turbine into two types of turbine. Okay, first is called the reaction turbine, and the second one is called the impulse turbine. So the way to differentiate between the reaction turbine and impulse turbine is that imagine that you have a water that has kinetic energy and also potential energy or flow energy. Okay, and then this water that has a lot of energy is going to be supplied into the turbine. Okay, and if the turbine is inside a casing, right, meaning that the flow energy is still conserved inside the water, right? It hasn't been completely transferred into kinetic energy yet when it's flowing. Okay, and when you put a turbine there, that turbine is called a reaction turbine. So reaction turbine is where you utilize both kinetic plus flow energy. Okay, and impulse turbine is a different story. It's a totally different story. Okay, imagine you still have that same water that has potential of flow energy and also kinetic energy, and then you're going to channel that water and convert all the potential energy into kinetic energy. Okay, and then you're going to channel it into a nozzle that sprays the fluid in the form of jet and hits the turbine. So this turbine is not actually inside a casing, right? It's outside. So all the flow energy has now been converted into kinetic energy, right? So I'm going to write it here. It depends on kinetic energy only. Don't worry if you don't understand yet, because later I'm going to draw some figures so you can distinguish properly between reaction turbine and impulse turbine. So right now, at this moment, we're going to move on to the reaction turbine first. Okay, so reaction turbine. And reaction turbine looks something like this. Okay, fair warning. Okay, it looks almost similar as the pump. It's just that the flow is on the opposite direction. Okay, so when you have a pump, remember that to solve the question related to pump, you have the velocity triangle, right, from inlet to exit. Okay, in reaction turbine, you will have velocity triangle as well. It's just that the direction is different, but the concept is still similar. I'll show you. Okay, so reaction turbine, it looks something like this. And if you notice, this is very similar with pump. You have impeller here. Okay, but this time the water comes from this side, and probably you have what you call the guide vein here. Okay, this guide vane is to guide the water so that it goes to the appropriate angle before it hits the turbine rotor. Okay, so water goes here and it goes into the impeller and it exits at the eye of the rotor. Okay, and this is what you call the guide vane. This is volute. Now we're going to call this runner. Okay, and it could also be called rotor or impeller, it doesn't matter. Only in this syllabus we're going to be using impeller for the pump, and for turbine we're going to be using the term runner. And then if I were to draw this as the side view, okay, and this is your volute, okay, this is where your rotor is and this is your exit. Okay, so this is your runner. Okay, so again this is runner, this is volute, and this is your exit, but the exit we call it draft tube. Okay, and this goes to atmosphere, and in case this is water, so this goes into the reservoir, and this reservoir we're going to call it tellurist. And that's how a reaction turbine looks like. And one type of reaction turbine is called the Francis turbine. Francis turbine. And this is the turbine that we are going to be focusing when we do the analysis. So before we go a bit further into the velocity triangle, I'm going to explain to you the energy conversion process from the fluid to the runner. Okay, so similar with pump, this is very related to the conservation of momentum, right? So the torque that is generated inside the runner is actually equal to rho Q R1 VT1 minus R2 VT2. Okay, and I think you can imagine what is VT1 and VT2. This is a tangential velocity of the absolute velocity in the velocity triangle component. This is still similar with the pump, only that the 1 and 2 is now reversed. Okay, so when you have torque, so you know that power is equal to omega times torque. Okay, so rotational velocity multiplied with torque. And if I put this equation there, so that's going to be rho Q times omega R1 VT1 minus R2 VT2, right? But omega times radius is going to be U. Okay, that is the blade speed. Okay, so again, rho Q multiply with U1 VT1 minus U2 VT2, right? And that's how you get the power inside the runner. Now, before we go any further into the equations, okay, let's draw the velocity triangle so that you can visually see what are the components inside these equations. Now, if I draw again the component inside the volute of the turbine, okay, it's going to look something like this. And here you have the guide vane, right? That's going to be guiding the flow into the runner. Okay, remember that guide vane doesn't move. Okay, guide vane is fixed in that position. There are turbines where you can change the angle of the guide vane, but guide vane doesn't rotate. Only the runner rotates. If this is rotating in clockwise direction, I'm going to label omega there. Okay, and inlet would be here at 1 and exit would be here at 2. Right? This is just the reverse of pump. Okay, for the pump, the inlet is at the eye, the exit at the outer edge of the diameter. But for turbine, because the flow coming in from this volute, okay, the inlet becomes here. Okay, and the exit is here. And if I take one runner, just as an example, if I take this runner, okay, and I'm going to zoom in and draw it bigger so that we can draw the velocity triangle. So if this is my runner, okay, let's give it some thickness. And now let's take a look at what the velocity triangle may look like. Okay, and I'm going to move this a little bit upward. Okay, so we can draw it more clearly. And of course, this is going to be your this is going to be your outlet, and this is going to be your inlet, right? And the blade is rotating this direction. That is your omega. Okay, now let's take a look at the inlet velocity triangle. Because it's a triangle, it has three components, which is the blade velocity, relative velocity, and also the absolute velocity. The velocity that is tangential to the rotor is the relative velocity. Okay, so in this condition, this is your relative velocity. Still remember what's the notation for relative velocity? It is a small v, right? Okay, so this is my small v. And of course, another component that you have is the blade speed. Now, because the rotational velocity is in this direction, I'm pretty sure that my blade will move from left to right. Okay, so this is going to be my U. This is U1. Okay, remember 1 is an inlet and 2 is an exit. This is just the reversal of the pump, but please don't get confused. Okay, now U1 in terms of vector, when you have the blade velocity, you add it with relative velocity, what you have is absolute velocity. Okay, now this is my capital V1. Okay, I'm going to put this like this for the small v. So now I have all the three components for the triangle. We know that the angle between the blade speed and absolute velocity is called alpha. So I'm just going to label it here. This is alpha. And the angle between my relative velocity and blade speed is called the beta. So where is our beta? Okay, so beta is actually, if I extend this line, so this is my beta. If I label this correctly, this is alpha 1 and this is beta 1. If I zoom in a little bit more and if I draw the line that is going to be perpendicular to the blade speed, okay, which is this line. Okay, and this makes the 90-degree angle. And you have to be careful here because this is quite a strange triangle compared to when we learn about pump. Okay, so where is my VT1 and VN1? So because the perpendicular line is here, right, my VN1 would be here. Okay, this is my VN1, right? And where is my VT1? My VT1 is all the way from here to here. This is my VT1. Okay, now remember VT1 and VN1 is just the component of V1. Okay, please remember that so you don't get confused within the triangle. Okay, now I think that's about it for the inlet velocity triangle. Let's take a look at what happens to the exit. Okay, remember what I told you before, that the velocity component that is parallel to the blade is relative velocity. So that's what we are going to draw first. Okay, so here the flow goes here to here. So guess what? This is your V2. This is the small V2, right? And then you have the blade velocity, which is going from left to right. Okay, so this is your U2. Okay, and U2 plus V small 2, you get the capital V2, that is your absolute velocity at exit, right? And as usual, between absolute and blade velocity, you have the alpha 2, and between the relative velocity and the blade velocity, you have the beta 2. Of course, for the triangle that looks like this, it's quite easy to determine where is your Vn2 and Vt2, the normal and the tangential component. So this is obviously V normal 2, and this is obviously Vt2. So that's it, guys. That is your inlet velocity triangle and also exit velocity triangle. So now I'm going to move a little bit further to continue our equation, that is P equal to omega T and P equal to this equation, that is rho Q U1 Vt1 minus U2 Vt2. Now, relative to the velocity triangle, now you know exactly where is Vt1 and Vt2. And this power is actually called the power at the turbine, okay, which is W dot T. This is the actual power at the turbine. And similarly, with the pump, okay, we have the efficiency. So, when the energy is transferred between the fluid to the runner, some energy will be lost. Okay, if I draw the illustration here, so this is your fluid and this is your runner. Okay, and when the energy is transferred between fluid and runner, some are lost. Okay, we're going to call it HL. Okay, the original power inside the fluid is called W dot F, and you're going to find it using rho GQ HT, and HT is the actual head drop inside the turbine. Okay, and for runner, okay, the power at the runner is actually this power. Okay, WT. Okay, and WT, as we know, is omega times torque. Okay, and from this illustration, I think you can imagine that the work of the fluid is going to be higher than the work of the turbine. So the efficiency of the turbine is going to be represented by W dot T divided by W dot F. Okay, it cannot be more than 1, right? So W dot T is omega times torque, and W dot F is rho GQ HT, which is the head drop. Let's say we want to find out what is Q. Okay, and based on this velocity triangle at inlet and exit, you know that Q is simply velocity times area, and velocity must be normal to the inlet or exit surface of the runner. So velocity, if you are looking at inlet, has got to be Vn1, or if you are looking at exit, this has got to be Vn2, and the area, similar with the pump, is actually 2 pi R1 B1. B is the thickness or the width of the runner, 2 pi R1 B1, and if you are looking at exit, so this is 2 pi R2 B2. Okay, so let's say you are looking for Vn1, for example, that's going to be Q divided by 2 pi R1 B1. Okay, and if we are looking for the, let's say we are looking for the relationship between Vn1 and Vt1. Now I know that Vn1 and Vt1 can be linked with alpha 1. Okay, so it's going to look something like this. So Vt1 equal to, this is Vn1 cotangent alpha 1. Vn1 cotangent alpha 1. Vt1 is actually spanning the whole distance here. Okay, so Vt1 is actually the addition of U1 plus whatever this distance is. Okay, and this distance is actually Vn1 cotangent beta 1, if you notice. Okay, so I'm going to write it here. Vt1 is also U1 plus Vn1 cotangent beta 1, right? And if I were to combine these two equations, okay, so I will have Vn1 cotangent alpha 1 equal to U1 plus Vn1 cotangent beta 1, right? And if I want to replace Vn1 with this equation, okay, I'm going to have Q over 2 pi R1 B1 cotangent alpha 1. I know that U is actually omega times R. So U1 is omega times R1 plus Vn1 again is Q over 2 pi R1 B1 cotangent beta 1. If I want to make this cleaner, I'm going to transfer this. Everything, I'm going to transfer it to the right hand side. So I'm going to end up with cotangent alpha 1 equal to 2 pi R1 square B1 omega divided by Q plus cotangent beta 1. Does it make sense? So this will be my final equation. So guys, what is the equation telling you, right? So this equation tells you the relationship between alpha, rotational speed, the discharge, and also beta. So this means that, let's say we're gonna fix the omega. Okay, let's say omega is fixed. Okay, so what's left is the relationship between alpha 1 and also Q, because beta 1 will follow alpha 1. So whenever you have changes in Q, okay, what you need to do is to adjust alpha 1. Right? And what do you need to do to adjust alpha 1 is by changing the angle of the guide vane. So the guide vane can be open or closed. Usually the guide vane is pivoted at one point, which allows it to rotate along this axis. Okay, so it can open and close, right? And the opening and the closing depends on the flow rate that the turbine needs to take, and that's exactly what this equation is telling you. So similar with pump, which has the theoretical head discharge curve, turbine also has its own performance curve, and the performance curve for turbine is a bit different than pump. So I'm going to draw one curve for you so that you can see. Okay, so in the x-axis you will have speed in RPM, and in the y-axis is the flow rate. See, it's a bit different than pump, right? So the performance curve for pump looks something like this. Okay, but performance curve for turbine looks something like this. And you have a few lines depending on the guide vane opening. Okay, remember this depends on the alpha one. Okay, so you have a few lines. Okay, so one line, two line, and three lines. Okay, and let's say that this is when the guide vane opens at 20 degree, this is 30 degree, and this is 40 degrees. And turbine also has efficiency, right? So this is the efficiency of the turbine. This efficiency will also be different at different operating condition of the turbine. And therefore, when you plot the efficiency on top of this graph, okay, you will have something that looks like this. Alright, so this will be your efficiency curve. So the highest efficiency would definitely be in the middle. Say this could be 90% efficiency, and this could be 80%, and the outer region could be 60%. Okay, so ideally, you want to install the turbine when you have the operating condition exactly here. Okay, the higher the efficiency of the turbine, the more energy that you can extract from the fluid. Okay, so that's the importance of this curve. Of course, there are several factors that impact the efficiency of a turbine. For example, of course, you may have separation, right? Separation flow, where the flow detached from the surface of the blade, thereby blocking the pathway. Okay, so the primary flow is actually blocked by the separation inside the passage. So if you have the passage that looks like this, okay, so if you have the flow coming in, let's say like this, and you have the separation developed here, okay, so this region is basically unusable at all for the primary flow to go through. So this means you have blockage, and that definitely can reduce the efficiency. And of course, another reason for inefficiency is the mechanical. Because this is a mechanical object, it has to rotate, so it sits on a bearing. Okay, so this bearing might have inefficiencies. You may also have frictions on the other parts of the turbine. Okay, so these are the three main reasons why the turbine has inefficiency. So I think that's a lot for you to take in. Okay, the reason why I go quite fast this time, because you already know pump. Okay, a lot of concept from pump can be used for the turbine. It's just in different direction. Okay, which I will show you later when we do the tutorial. Okay, so please go over this lesson again and again until you understand the difference between a pump and a turbine. And the next video, we're going to do tutorial about Francis turbine. So that's it from me this time. I'll talk to you soon. Bye.